Hello everyone, welcome to section 4, part 2 of Abstract Modern Algebra. So in this part we will look at the theorems that we looked at in part 1 and just look at the proofs behind them. So if you don't want to watch all the proofs for these, because that's going to be all this you're going to see in this video, then you can just skip and go to the examples. But if not, then I'm glad you are here to watch the proofs because it can be great to look at the logic and the reasoning behind these theorems and why they work. So let's take a look at our first theorem. And our first theorem is products of disjoint cycles. And the theorem states that every permutation of a finite set can be written as a cycle or a product of disjoint cycles. So let's write this proof. And this proof is let alpha be a permutation on the set A equals 1, 2, all the way to n. So now let's let A2 equal the permutation alpha A1 and A3 equals alpha of A1, which equals alpha squared of A1 for some A1 and A. Then we have A1 equals alpha m of A1 for some natural number m. So we must eventually have a repetition say alpha I of AI equals alpha j of A, sorry, it's supposed to be A1 of A1 for some I and j that are natural numbers and I is less than j. So thus m equals I minus j, and we can express the sequence A1, A2, so on and so forth up to AM as alpha equals A1, A2, so on and so forth up to AM. Then we'll put 3 additional dots here at the end where the 3 dots at the end show the possibility that we may not be using all of the set A. Okay, so now let's choose an element B1 in A, and let's let B2 equal permutation alpha B1, B3 equals alpha squared, B1, so on and so forth, where B1 equals alpha k B1 for some natural number k. So now let's suppose this cycle has elements in common with our last cycle. Then we have alpha I of A1 equals alpha j of B1. So alpha I minus j of A1 equals B1, and thus B1 equals AT, where T is a natural number. However, this is a contradiction. So therefore, our permutation is alpha equals A1, A2, so on and so forth, up to AM, B1, B2, so on and so forth, up to, do we define it as, we have it as K, so this will be BK, and then so on and so forth. As desired. All right, that is it for our first theorem. So let's take a look at our second theorem. We have disjoint cycles commute. So the theorem is if the pair of cycles alpha equals that sequence A1 up to AM, and beta equals the sequence B1 up to Bn, have no entries in common, then alpha beta equals beta alpha. All right, let's look at the proof for this. So let's let alpha and beta be permutations of the set S equals A1, A2, AM, B1, B2, be n, C1, C2. Let me erase this in. There we go. Now it looks like a subscript. Up to CK. Where M, N, and K are natural numbers, and C's are the members members of S. Let's make sure we know they're of S. Fixed by alpha and beta. So now let's let A1 be an element of S. So, let's let AI be an element of S, where I is a natural number. Then we have alpha beta of AI equals alpha beta of AI equals alpha of AI equals alpha I plus 1. Since beta all A elements, we have beta alpha of AI equals beta of alpha of AI equals beta AI plus 1 equals AI plus 1. So now let's let CI be an element of S. Then we have alpha beta of CI equals alpha beta of CI equals alpha of CI equals CI, and beta alpha of CI equals beta alpha CI equals beta CI equals CI. So therefore, alpha beta equals beta alpha for all entries of S as desired. Trying to get my square filled in here. All right, yep, that is it for our second theorem. All right, the third theorem, we have the order of a permutation. So the theorem is the order of a permutation of a finite set written in disjoint cycle form is the least common multiple of the lengths of the cycles. All right, let's look at this proof. So suppose, let's not suppose, let's let alpha and beta be disjoint cycles of length m and n, not where, and k be the LCM of m and n, where k, m, and n are natural numbers. So let's see here. So then, let's scroll down. Then alpha raised to the k equals beta k equals epsilon, where epsilon is the identity permutation. So since alpha and beta commute, we can write alpha beta raised to the k equals alpha k beta k equals epsilon. So then the order of alpha beta, call it t, must divide k, where t is a natural number. However, alpha beta of t equals alpha t beta t equals the identity permutation. So since alpha and beta are disjoint, alpha t fixes the elements of beta, and beta t fixes the elements of alpha. So then it follows that alpha t beta t fixes 1 through n if and only if alpha t equals epsilon and beta t equals epsilon. So thus, t is a common multiple of m and n, and since k is the least common multiple of m and n, k must be less than or equal to t, and k equals t. So therefore, the order of a permutation of a finite set in disjoint cycle form is the LCM of its cycle lengths as desired. All right, that is it for that theorem. Now let's take a look at the next theorem that we have, the product of two cycles. So this theorem was every permutation in Sn the symmetric groups where n is greater than 1 is a product of two cycles. All right, let's take a look at this one. So the identity of two cycles can be expressed as 1, 2, 1, 2. We know that the sequence or the products A1, A2, so on and so forth, up to AK, and B1, B2, so on and so forth, up to BT, and then C1, C2, so on and so forth, up to CS, where K, T, S are natural numbers. And this was from, I believe it was the first theorem that we looked at for the product of disjoint cycles. Or for the, let me go back up and look at the name of it. Yeah, it's the products of disjoint cycles. Because we're looking at the products of two cycles now. So we can write it as A1, AK, A1, AK minus 1, A1, A2, B1, BT, B1, BT minus 1, so on and so forth. And then B1, B2. And then if we keep going, we will get to C1, CS, C1, CS minus 1, all the way to C C1, C2, which is a product of two cycles as desired. Okay, so if you remember, we also had a limit that went with this theorem, and the limit states that if the identity permutation epsilon equals beta 1, beta 2, so on and so forth to beta r, if it equals that product where the betas are two cycles, then r is even. Okay, so let's take a look at the proof of this lemma. So let's suppose that beta 1, beta 2, so on and so forth to beta r, where r is a natural number, is an odd number of two cycles that is epsilon the identity. So then r does not equal 1 since a 2 cycle cannot equal the identity permutation. So now let's let beta 1 equal AB. So now there must be a 2 cycle beta I where I is a natural number and I is greater than 1 that contains A. We may assume the product beta 1, beta 2, so on and so forth, up to beta r is 1 where an I is minimum and 1 with fewest number of A's as an entry in any cycle. So now let's suppose I equals 2. So then beta 1 and beta 2 has the form AB AB or ABAC, where C is not equal to B. So if AB equals epsilon, we can delete it, and then we have a product with an odd number of 2 cycles and fewer A's. However, we assumed that this product is one where I is a minimum, and it's one with the fewest number of A's, so this is a contradiction. So now, if beta 1, beta 2 equals ABAC, where B is not equal to C, then ABAC equals ACBC. So now let's let beta 1 prime, beta 2 prime equal ABBC. So we now have products beta 1 prime, beta 2 prime, so on and so forth, up to beta R prime with 1 fewer A than our previous product, which again is a contradiction. Let's see if I can fix this U right here. So now let's let I be greater than 2, and thus let's actually use then we have our product beta 1 prime, beta 2 prime, so on and so forth, up to beta I minus 2, and then beta I minus 2, beta I plus 1, so on and so forth, up to beta R is a product of R2 cycles since A is not an element of beta I minus 1. Let's see if I can make this a little cleaner. But C is an element of beta I minus 1. And A is in the first cycle and appears as an entry before the ith cycle of the product, which again is a contradiction with I. Whoops. Now let's say thus beta I minus 1 beta I equals DC AC, where D does not equal A in the product beta 1 prime, beta 2 prime, so on and so forth up to beta R, and beta I minus 1 prime, beta I prime equals AD DC. So now we can then obtain the product beta 1 prime, beta 2 prime, so on and so forth, up to beta I minus 1 prime, beta I prime, so on and so forth, up to beta R prime, which is a product of R2 cycles that is the identity and A appears in the first cycle and before the ith cycle, which again is a contradiction. So therefore, R must be even as desired. And yeah, that's pretty much all there is to this proof. It's just looking at different conditions for what this could be, but by showing contradiction for all these statements, we find that R must be even. All right, let's take a look at the next theorem, even and odd permutations. So let's see here. Here we are. So This theorem states that if a permutation alpha can be expressed as a product of an even or odd number of two cycles, then every decomposition of alpha into a product of two cycles must have an even or odd number of two cycles. All right, let's look at the proof for this. So let's let a permutation have the products beta 1, beta 2, so on and so forth, up to beta r, and let's do gamma 1, gamma 2, up to gamma s, where r and s are natural numbers. So then we can find that epsilon equals gamma 1, gamma 2, so on and so forth, up to gamma s, and then beta 1 inverse, sorry, it's supposed to be beta r inverse, so on and so forth, up to beta 2 inverse, beta 1 inverse is equal to beta 1, gamma 2, so on and so forth up to gamma s, and then beta r, so on and so forth up to beta 2 and beta 1, since a 2 cycle is its inverse. So from the previous lemma, if s plus r are even, then r and s are both even or odd as desired. So yeah, this proof just builds off of the lemma that we went over, and this is how we developed how the idea was developed that an even or an odd permutation can be determined from its 2 cycles, how many 2 cycles that it has. All right, so the next theorem that we looked at was even permutations form a group. And this theorem states that the set of even permutations in Sn forms a subgroup of Sn. Well, for this proof, we'll have to do a subgroup test for this set of even permutations, and we'll use the 2-step subgroup test for this. We'll show that the set is non-empty, that it has A, B when A and B are in the group, or in this case, we're doing composition, so we'll do alpha, beta when alpha, beta is in the group, and then we'll have alpha inverse when alpha is in the group. So let's let A of n, let me see if I can fix this, A of n represent the set of even permutations in Sn, where n is a natural number. So let's scroll down here. Since AN is a subset of SN, and epsilon is an element of Sn. The identity 0 is in AN, since 0 is an even permutation. So thus, A of n is non-empty. So now let's let alpha and beta be permutations of A of n. So then alpha has 2k products, and beta has 2j products, where k and j are natural numbers. Let's see if I can get my page turned. There we go. So we have alpha of beta equals 2k plus 2j, which equals 2k plus j. And since 2k plus j is even, alpha of beta is an element of A of n. Okay, now let's let alpha be a permutation of A of n. So then we have alpha equals A1, A2, so on and so forth, up to A of 2k products, where k is a natural number. So we have alpha inverse equals to A of 2k, so on and so forth, up to A2, A1. So hence alpha inverse is even, and thus alpha inverse is in A of n. So therefore, A of n is a subgroup of S of n as desired. Yep. So we just applied a two-step subgroup test, and we were able to prove that A of n was a subgroup of S of n. Well, all right. So let's take a look at our last theorem here. So our last theorem is that for n greater than 1, a of n has order of n factorial over 2. All right, so to prove this, we will have to look at some cases, just 2 cases. So let's let alpha be a permutation. We proceed by cases on alpha. So let's take a look at case 1. We are going to look at where alpha is odd. So then the permutation 1, 2 alpha, or the identity times alpha, is even, and 1, 2 alpha does not equal 1, 2 beta when alpha does not equal beta by cancellation. Where beta is a permutation. So there are as many even permutations as there are odd permutations. Okay, so now let's take a look at case 2. And it'll just be where alpha is even. So now, then the permutation 1, 2 alpha is odd, and one, 2 alpha does not equal 1, 2 beta when alpha does not equal beta by cancellation, where beta is a permutation. So there are as many odd permutations as there are even ones. So therefore, since we have an equal number of even and odd permutations the order of A of n equals n factorial over 2, since the order of Sn equals n factorial, as desired. All right, that is it for all the theorems and proofs behind them for section 4 of Abstract Modern Algebra. Thank you guys so much for watching, and I will see you in the examples video for this section.